to the Section 7.1 video lecture. I am Dr. Scott Spaniel, as ever, your instructor for statistics at Morton College. And so what we're going to do today is start talking about Chapter 7. So in Chapter 6, we looked at discrete probability distributions. And so in Chapter 7, we're going to look at continuous probability distributions, and specifically two types. The first is the uniform probability distribution, and then the normal probability distribution is the second one. And we're going to introduce both of those in this first section. Now, the uniform probability distribution is nice because it's easy to understand how this works. It's a nice way to practice the idea of how a continuous probability distribution works. And then the normal distribution is really important because we're going to use it a lot in the last portion of this class in chapters 8, 9, 10, and 11. So go ahead and take out the new note sheets, and we're going to turn to the very beginning to get started. Okay, so let's get started with this. So Chapter 7 handout. So the first section is called Properties of the Normal Distribution, but we're not actually going to start with the normal distribution. We're going to start with the universal distribution here in a second. So when every outcome has an equal probability of occurring, the random variable x is said to follow a uniform probability distribution. A good example of this is something like rolling a die. Okay, that has 6 outcomes. All the outcomes are equally likely, so that is a uniform distribution. Now, that is a discrete uniform distribution, so that's not what we're going to be necessarily talking about here, but that's a good idea to think about. Something where all of the outcomes have the same probability of occurring. A probability density function, PDF, but not that kind of PDF that I'm currently writing on, but we call it a PDF, is an equation used to compute probabilities of continuous random variables. It must satisfy the following two properties. The total area under the graph of the equation over all possible values of the random variable must equal 1. So the entire area under the curve is 1. And the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. That is, the graph of the equation must lie on or above the horizontal axis for all possible values of the random variable. Okay. So if we're looking at a uniform random variable, that means the height, the probability of each value has to be the same. So that means the height of the graph is the same across the whole thing. So it has to make a shape that looks like this. It has to be a rectangle. Okay. So what we say is the left side of the rectangle is the smallest value that the random variable can have. So in this case, we'll call that A. And the right-hand side is the largest value the rectangle can have. And so that gives us the base here is the width of our rectangle. Now, if we recall, the total area from up here has to be 1. So the key is, well, what's our height? Well, rectangles have a formula for area that equals length times width, right? So in this case, we know 2 of these variables, so we can actually solve for the last one. Or a better way to write that for this might be area equals base times height, right, for the way we're looking at this. Although I'm going to change my mind a little bit here, and I'm going to use capital B, else that might get confusing because I have another B down here. So let's do, or actually, I'm going to change my mind completely. And let's do height times width. Okay, so let's call it the width and the height of this rectangle. So what we can do is substitute in the things we know. Well, we know from up here, from number 1, that the total area has to be 1. So that means the area is 1. And we know the width is the difference between A and B. So this would be H times B minus A, right? The difference between A and B. And so then if I solve for H by dividing both sides by B minus A, I get 1 over b minus a, and then on the right-hand side, the b minus a's cancel, and we get h. So the height of this rectangle just has to be 1 over b minus a. So when you're making a uniform probability distribution, the height is always the reciprocal of the width. It's always 1 over whatever width there is. Okay, so let's look at an actual example of this to practice with this. So this says the reaction time of a certain chemical process follows a uniform probability distribution with 5 less than or equal to x, which is less than or equal to 10. Draw the graph of this density curve. Okay, so it's uniform, which means we know it's going to be a rectangle that goes from 5 to 10. And then the key is, well, what's the height? Well, the height, we said, right, is 1 over the difference between the starting point and the ending point. So in this case, that's 1 over 10 minus 5, which is 1 over 5. So the height, so our rectangle is 1/5. So okay, so that's the setup. Then if we look back here, right above this problem, it says the area under the graph of a density function over an interval represents the probability of observing a value of the random variable in that interval. So if we take an interval, say 6 to 8 minutes, and so let's just redraw our graph here to do this problem. So there's our height, and then, whoops. Okay, we go from 5 to 10. And we want to look for an interval inside of that. We want to go from 6 minutes to 8 minutes. Okay, so in order to find the probability, we want to find the area of this shaded region. Well, how do we find area? We find the length of the width of the base times the height. So in this case, the area, which is going to be our probability of between 6 and 8 minutes, is our height, 1/5, times our width, which is 8 minus 6. So that's 1/5 times 2, which is 2/5. So our area in this case would be 2/5. So that means the probability of getting between 2 and 5, between 8 and 6 and 8 would be 2/5, 2 out of 5. Okay. So the next one says, what is the probability that the reaction time is between 5 and 8 minutes? So I don't have to keep drawing the graph, right? The probability is going to equal the height, which stays the same, 1/5, times the difference between my two endpoints. So in this case, 8 minus 5. So that's 1/5 times 3, which is 3/5. And then the last one says, what is the probability that is less than 6 minutes? So that's the probability. It's going to be 1/5 times, well, in this case, less than 6 minutes would mean between 6 and the end. So 6 minus the end point of my region, which is 5. So that's 1/5 times 1, which is just 1/5. Okay, so that's the idea here. So what I'd like y'all to do now is flip over to this next page, pause the video for a moment, and try doing these problems on page 3, and then we'll go through them together. Okay, so now that you've had a chance to try this, let's go through it together. So in this case, if we draw our curve, our region goes from 0 to 30, so our rectangle looks something like this. And so the height of our rectangle is 1/30, right? Because the difference between 30 and 0 is 30, so 1 over 30. So then what's the probability your friend is between 5 and 10 minutes late? So we take the height times the width of the region, which is 1/30 times 5, which is 1/6. Okay, so that's all we're really doing here. So then what is the probability that your friend is between 15 and 25 minutes late? So that's 1/30 times 25 minus 15. So that's 1/30 times 10, which is 1/3. What is the probability that your friend is at least 20 minutes late? So at least 20 minutes late in this case, because our whole region only goes up to 30, would be 1/30 times 30 minus 20, which is 1/30 times 10, which is 1/3. So notice these last two problems had the same width, therefore they have the same probability of occurring because this is uniform. So anything with the same width will have the same probability of occurring. And then the last one says, what is the probability that your friend is no more than 5 minutes late? So that would be between 0 and 5 minutes late. So 5 minus 0. So 1/30 times 5, which is 1/6. Okay, and so that's really all there is to the uniform probability distribution. So we use this idea that the height is the same everywhere, and that the area has to add up to 1 to figure out the height. And then we can just multiply height times the width of the region we're looking for. Okay, so that's the idea. So now what we're going to do is we're going to take that idea and we're going to expand it to what's called the normal curve. So this idea of area is still going to be true, but unfortunately the height is not going to be uniform, so it's going to be a little more complicated to calculate these areas. And in the next section, we'll talk about how to do that, and what we're going to use is our graphing calculators and a function called the normal PDF and normal CDF. So relative frequency histograms that have a shape similar to the following are said to have the shape of a normal distribution. So graphs that have a fairly bell-shaped shape are what we're calling normal distributions. So first thing we just want to be able to do is recognize things that are approximately normal. So if we look at this first one here, that looks like a bell shape to me, so that's approximately normal. Okay. The second one here obviously doesn't make a bell shape, right? Because it's skewed to the left over here, right? A bell would need to look something like this. And there's no data over here, so it's not bell shaped, so this is not approximately normal. Okay. So that's the idea. So take a look at these next two. Pause the video for a second if you need to, and tell me whether you think they're approximately normal or not. Okay, so now that you've tried these, this first one is not, right? Because it's skewed to the right, so that's not approximately normal. And this last one does look like a bell shape, so that one is yes. That is approximately normal. Okay, so now that we know how to recognize things that look like normal distributions, let's talk about some of the properties of normal distributions on the next page. So the normal distribution is symmetric about its mean, mu. Okay, so notice mu is this highest point. Because mean equals median equals mode, there is a single peak at the highest point, which occurs at mu. Okay, so there's a single peak for a normal distribution that happens at the mean. It has inflection points at mu minus sigma and mu plus sigma. So that's plus and minus 1 standard deviation from the mean. And what a inflection point means, if you look at the picture up here, these are the inflection points. It's where the graph goes from increasing faster and faster and faster to starting to curve over the top. Okay, and then the vice versa. So you're, instead of continuing to rise, like if we didn't have an inflection point, the graph would look like this. It would just keep going up like that. Or this one, if we didn't have an inflection point, would just keep going down. But the inflection point is when that curve changes and curves back the other way. And with a normal curve, those happen at plus or minus 1 standard deviation. Okay. The area under the curve is 1. Just like any other probability density function, the area under the curve needs to be 1 because the total probability of any experiment is 1. And the area under a density curve is the total probability. So therefore, since this is symmetric, the area under the curve to the right of mu equals the area under the curve to the left of mu, and that area is 1/2, or 0.5 if we want to write it as a decimal. So half of the area is to the right of mu, and the other half of the area is to the left of mu. Okay. As x increases without bound, the graph approaches but never reaches the x-axis. And the same is true in both directions. So the graph gets closer and closer and closer to this x-axis here. This is the x-axis, this horizontal line, but it never actually gets there. Okay, there's always at least some minute amount of space between the graph and the axis. And because this is bell-shaped, the empirical rule applies. So 67% of the area under the normal curve is between mu minus 1 sigma and mu plus 1 sigma, right? This is something we talked about back in chapter 3. Approximately 95% of the data is between 2 standard deviations from the mean, and approximately 99.7% of the data is within 3 standard deviations of the mean. Okay. So based on all that information, there's a few things we ought to be able to do. One is we ought to be able to look at a normal curve and know what the mean and standard deviation here is. So for this first one, the mean is the highest point, which is 100. And then we know that 1 standard deviation is the inflection point. So the inflection points in this first case are there and there, which if you notice are 15 units from 100, right? 100 minus 85 is 15. 115 minus 100 is 15. And so the mean was 100 and the standard deviation is 15. Okay, so that's the idea there. So pause the video for a second and try this other one. Tell me what the mean and the standard deviation are. Okay, so now that you've had a chance to try that, you should see that the peak is at 530, so that's our mean. And the inflection points are at 430 and 630, which are 100 units away from our mean. So our standard deviation is 100. Okay. So now what we're going to use this for, starting in the next section, is to talk about areas under the curve, which are going to allow us to talk about proportions and probabilities. So the area under a normal curve. Suppose that a random variable x is normally distributed with mean, mu, and standard deviation sigma. The area under the normal curve for any interval of values of a random variable x represents either the proportion of the population with the characteristic described, so the percentage of the population that has the characteristic, or the probability that a randomly selected individual from the population will have the characteristic described by the interval of values. Okay, so let's look at an example of what that means. So monthly charges for cell phone plans in the United States are normally distributed with a mean of 62 and a standard deviation of 18. So we can use that to draw a normal curve. So I went ahead and gave you a normal curve just to make things easier. But now what we want to do is we want to label it. So we can label the mean at the highest point in the middle here, which would be 62, so that's $62. And then we can label the inflection points at 1 standard deviation below and 1 standard deviation above the mean. So 62 minus 18 is 44. So that's on this next tick mark to the left. And 62 plus 18 is 80. And then these tick marks are evenly spread out, and standard deviation stays the same, so we can fill in the next 2 standard deviations in each direction by just repeating what we just did. So to go to the left, we just subtract 18. So 44 minus 18 is 26, and then 26 minus 18 is 8, and then 80 plus 18 is 98, and 98 plus 18 is 116. Okay, so that's what they mean by draw the normal curve with the parameters included. So now what they'd like us to do is shade the region that represents plans that charge less than $44. Okay, so we just go into our graph, we draw a vertical line at 44, and then we shade all the things that are less than 44. So that's everything to the left. So if I was trying to find the probability or the proportion of people who had a cell phone plan that was less than $44, that would be this area. And that's what the rest of this problem says. So it's supposed that the area under the curve at x equals 4 to the left of x equals 44 is 0.1587. Provide 2 interpretations of this result. And that's where these bullet points come in. So the 2 interpretations would be that 15.87% of cell phone plans cost less than $44 a month. Okay, so that's one way, right? It's a proportion of the population, which is a percentage of the population. And the other option is that it's a probability. So we could say there is a 0.1587 chance of randomly selecting a cell phone plan that costs less than $44 a month. Okay, so in the next section, when we learn about how to use our graphing calculators to calculate these things, that's what we're going to be trying to find out, either the proportion of the population that has a characteristic or the probability of something happening. Okay, so at this point, go ahead and flip over to the next page and try doing this exact same thing that we just did, and that'll be the end of the section. Okay, so now that you've had a chance to try this on your own, let's go ahead and run through it together. So we've got a mean of 14 years, so that goes right here in the middle, and then we've got a standard deviation of 2.5. So to fill in the rest of these, we need to subtract 2.5 going to the left and add it going to the right. So if we subtract 14 minus 2.5 is 11.5. 11.5 minus 2.5 is 9, and 9 minus 2.5 is 6.5. And then if we add it going the other direction, 14 plus 2.5 is 16.5. 16.5 plus 2.5 is 19, and 19 plus 2.5 is 21.5. So there's our curve. And it says shade the region that represent the proportion of refrigerators that last more than 17 years. So 17 is here just to the right of 16.5, so we draw a vertical line at 17. And then we want it to last more than that, so more than 17 would be to the right. So we shade to the right. So suppose that area is 0.1151. Provide two interpretations of this result. Well, interpretation 1 is 11.51% of refrigerators last more than 17 years. And interpretation number 2 is that there is a 0.1151 chance of randomly selecting a refrigerator that lasts longer than 17 years. Okay, so that's it for section 7.1. That's about how these density functions work. And so in the next section, we're going to look at how to calculate these areas. So thanks for watching this video, and I'll see you next time. Don't forget to do your assignments, and feel free to reach out to me via Remind or email if you have any questions.